Hi everyone! Today we're going to be talking about intermolecular forces. Basically, what we're trying to figure out here is how molecules stick together. And what it comes down to is electrostatic attraction. Essentially, when you have things of opposite charges, they attract. We talked about this when we learned about ionic compounds. And that is essentially what's going on here, except that our charges are much smaller than they are on ionic compounds. When you're talking about covalently bonded molecules, those molecules might have a dipole. And so that dipole is going to have a slight negative charge at one end and a slight positive charge at the other end. And really, that tends to be the basis for everything we're talking about. Intermolecular forces are forces between molecules that hold solids and liquids together. And so if you think about something like HCl, that has a covalent bond that holds the hydrogen and the chlorine atoms together, and that's a pretty strong bond. But if you have a bunch of HCl molecules together, because those things have dipoles, you're going to get this electrostatic attraction that holds the positive end of one to the negative end of another, and that is our weak intermolecular force. It's an attraction that holds things together, but because it's so much weaker, it's easy to break. The covalent bond between the hydrogen and the chlorine is hard to break. The attraction that holds two HCl molecules together is a lot easier to break. So that's what we're talking about. Again, the basis of all intermolecular forces is an attraction between different sorts of charges. Right? So you know that negative and positive things attract. It's very similar to what you see in a magnet, where if you put opposite poles together, they move together. If you get the same charge or the same pole of a magnet together, right, then they repel from each other. Now, we can look at this from a fairly mathematical point of view. I'm not really going to dive into that. To do that properly, take a physics class on electromagnetism. So I put a simplified version here. The proper version has vectors and stuff in it. And if you're really interested, I advise you, like I said, to go take a physics class. And there's also a constant in there that we're not going to worry about right now. But basically what we have is this. We have the electromagnetic force. How strong is that? It's proportional to, that's what that little squiggly thing means. The magnitude of the charges that are interacting with each other, how big are those charges, divided by the distance between the charges squared. So the bigger the distance, the smaller the pole. The smaller the distance, the bigger the pole. The bigger the charges, the stronger the force. The smaller the charges, the smaller the force. And so you can really think about this as it's the charges over the distance, and that is sort of a simplification that we're going to use right now. Now, when it comes to intermolecular forces, we're mostly worried about the magnitude of the charges. Those distances are not going to change a lot. They're not going to change enough to make a substantial difference. How strong are the charges? That's what it comes down to. So some people say that there are 3 intermolecular forces. I like to say there are 3.5. I know it sounds kind of dumb. How can you have half a force? But you'll see what I mean. So the first thing we're going to talk about is we're going to talk about ion-dipole forces. For an ion-dipole force to exist, you need to have, number 1, ions, and number 2, surprise, something with a dipole, basically a polar molecule. So essentially what's happening here is you have a bunch of ions that are either positively or negatively charged. And of course, you're going to have a mixture because we have electrical neutrality in any given system. And so you have the ions, and then you have the dipoles, whatever those dipoles are, arranging around the ions. In the case of the cations, we're going to have the negative ends of the dipoles arranging themselves around the cation. And in the case of the anions, the positive ends of the dipoles will arrange themselves around the anion. Negatives attracting positives and vice versa. The second sort of intermolecular force we're going to talk about we call dipole-dipole forces. And here we have an interaction between two polar molecules, where you have something that has a dipole, and it will interact with something else that has a dipole. There will be an attraction when you have two things arranged in such a way that the negative part can attract to the positive part. And there are a whole bunch of ways that this can happen. Now, of course, it's rarely just one molecule attracting to another single molecule. There's usually a whole bunch of molecules. And so you can see in this particular case, we've got a whole bunch of possible attractions here between negative and positive ends. But we also have a whole bunch of things that can push each other apart. Where these orange dotted lines are, we have negative things repelling from negative things and positive things repelling from positive things. You have both attractive and repulsive forces going on at any one time. But the thing about having both of these forces exist, the attractive forces hold together and exist for a long time, whereas the repulsive forces push each other away, increase the distance so that force goes down. So that drops off very quickly. Overall, there's going to be net attractive forces in things where you have two dipoles. So how strong are these things? Well, that depends on the magnitude of the charges, right? So it really depends how strong are those dipoles. How much are electrons pulled to one side of the molecule versus another? That really depends on the electronegativity, the magnitude of the dipole moment. And it tends to be something between 1 and 4% of a covalent bond. So even a very strong dipole-dipole force is just going to be really, really small compared to a covalent bond strength. So I said there were 3.5 forces. Here's our half force. Some people call this its own separate force, but I don't think it is. I call hydrogen bonding a subset of dipole-dipole forces. And the reason I do that is because they behave exactly the same way. So think back to electronegativity, as we talked about in the previous video. Remember that the strength of a dipole is dependent on the electronegativity difference. So hydrogen bonding occurs when we have hydrogen, which is pretty much the lowest electronegativity thing we can have that doesn't prefer forming ionic compounds. And we're going to match it up with something that is very high electronegativity. Hydrogen bonds occur between very strong dipoles with very large electronegativity differences. And so what we have is nitrogen-hydrogen, oxygen-hydrogen, and hydrogen-fluorine. Some people, not everyone, are going to throw in hydrogen-chlorine bonds. Those also have a very strong dipole. But just FYI, because of electron configurations, both HF and HCl bonds only occur in the HF and HCl acids. They don't occur in any larger molecules. So really what you're looking for is you're looking for an NH or an OH bond in a molecule. The last of our 3.5 intermolecular forces is what we call London dispersion forces, sometimes also called London forces, dispersion forces, or van der Waals attractions. So there's a whole bunch of names for these. I usually call them either LDFs or dispersion forces. These are probably the hardest for people to understand, and that's because they occur in molecules that don't have polar bonds. So what happens? Remember that an orbital is essentially a probability distribution, and you usually have two electrons floating around in that orbital, and they are moving independently of each other. So because they're moving independently, there's a chance that they could both end up on one side of the molecule at the same time. Here I've got helium to show you. It only has 2 electrons, so it's really easy to see. Here's my electrons, both on one side of the molecule. This is an instantaneous unevenness in the distribution of electrons. It's instantaneous because those electrons don't just sit there on one side. They keep moving. Electrons move very quickly. But while they're over there for a short time, we're talking like nanoseconds, picoseconds maybe even, we're going to have what we call an instantaneous dipole, where we have a small negative charge on one side of the molecule and a small positive charge on the other side of the molecule. Now, if that atom happens to be next to another atom, what can happen is, because you have that positive charge, very small positive charge, but a positive charge on one side of the atom, that can actually pull electrons towards it in the adjacent atom. And we call that an induced dipole. And so it's going to pull electrons to one side, and that will give it a partial negative charge. And guess what? Now we have a partial positive charge, a partial negative charge that are connecting with each other. And that's the force. That's where the force comes from. It comes from random distributions of electrons that affect the distribution of electrons in adjacent molecules. So London dispersion forces are affected by a couple of things. First of all, how big is the electron cloud that surrounds the molecule? That depends on how big your molecule is. The bigger the molecule is, the more likely you are to have uneven distributions of electrons, and the more likely you are to get a London dispersion force forming. London dispersion forces operate between all molecules, whether they're polar molecules or non-polar molecules. But here's the thing. If you have two polar molecules interacting, you're always going to have that dipole-dipole force pulling them together. You're not going to always have the London dispersion forces. Those are going to come and go, and they're much, much weaker. So it's a bit like having a parent and a toddler carrying a piece of furniture into the house, right? The parent picks it up and the toddler says, "I help," and puts a hand underneath. But we all know who's really carrying the piece of furniture, right? In this particular case, there's the dipole-dipole forces and the little toddler London dispersion forces that are both holding these two together. But we all know which is doing the real work. And so the strong forces holding it together are really the dipole-dipole forces. Okay, quick summary of intermolecular forces. First of all, ion-dipole forces. Remember, you're going to need, for that, both a polar molecule and an ion. Dipole-dipole forces, you need two polar molecules. Hydrogen bonding. You need two polar molecules that contain a really strong dipole. And again, oxygen, hydrogen, nitrogen, hydrogen, fluorine, hydrogen, or also sometimes chlorine, hydrogen. London dispersion forces, basically everything has London dispersion forces. So people ask me, how do you know what intermolecular forces are present in a system? It's not always easy to figure that out at first. It takes practice. And so what I'm going to do is I'm going to walk you through a couple of different scenarios. First of all, what if you have a pure substance? What intermolecular force is operating between molecules of that substance? Basically, what I'm going to do here is I'm going to show you a flow chart. And we always are going to start with this question. Does that molecule have a dipole? In this particular case, we're talking about molecules of the same substance. So every molecule is going to answer the same to this particular question. If there's no dipole, the only force that can occur in that system is London dispersion forces. What if it does have a dipole? If it has a dipole, the next thing we're going to ask is it a strong dipole? Like oxygen-hydrogen bonds or a nitrogen-hydrogen bond. If you don't see one of those bonds, you have a dipole-dipole force. If you do have some of those bonds present, then what you're going to get is you're going to get hydrogen bonds. So really quickly, let's look at the intermolecular forces between molecules of the same substance. And we're going to start with carbon tetrachloride. Does the molecule have a dipole? We saw in the last video that it doesn't. So that's London dispersion forces. That's all you'll find in carbon tetrachloride. What if we have trichloromethane, also called chloroform? We also looked at this one in the last video. Does the molecule have a dipole? It does. The positive end of the molecule is up by the hydrogen carbon area and the negative end down by the chlorines, remember. So we do have a dipole. Now, is that a strong dipole like nitrogen, hydrogen, or oxygen, hydrogen? And the answer is no, it's not. It is a carbon-chlorine bond. Remember, I said that the hydrogen-chlorine bond was, something that people said maybe, maybe not. But carbon-chlorine is not going to be strong enough to give us a hydrogen bond. It does not have that. And so what we're going to get is we're going to get dipole-dipole forces. And essentially what we're going to see is we're going to see molecules arranging themselves this way. And so you can see the positive ends are going to match up with the negative ends and vice versa. Now, what if you have a mixture of molecules of different sorts? In that case, we're going to need to use a different flow chart. Again, we're going to start with a similar question to what we were doing before. Do some of the molecules have a dipole? If the answer to that question is no, if none of the molecules have a dipole, there's only one thing that can be holding them together, and that is London dispersion forces. But what if some of the molecules do have a dipole? The next thing we need to ask is, are there ions present? So you could have a dipole and some ions. If that is the case, what we've got is we've got ion-dipole forces holding things together. What if there are no ions? Well, the next thing we're going to ask is, do all of the molecules have a dipole? So you could have a mixture of something like, let's say, water, which is polar, and hexane, which is not polar. So that would mean that some of the molecules, the water molecules are polar, the hexane molecules are not polar. What happens if you don't have all of the molecules with dipoles? Well, you can't get any other force other than London dispersion forces. What if you do end up with all the molecules having a dipole? So now we're back in familiar territory, because the next thing we're going to ask is, do all of the molecules have a strong dipole like NH or OH? And hopefully you know where this is going. If yes, the answer is you've got hydrogen bonds. If no, we're left with dipole-dipole forces. Now, very importantly, all of the molecules have to have that strong dipole. You can't have something that has a strong dipole, an oxygen-hydrogen bond, and then something that's got a weak dipole, like a carbon-chlorine bond. You put those two things together, you don't get hydrogen bonding. In order for hydrogen bonding to occur, everything in the system has to have those strong dipoles. So let's look at a mixture. Let's look at a mixture of trichloromethane and carbon tetrachloride. Do some of our molecules have a dipole? Well, we know that at least trichloromethane has a dipole. So the answer is yes. All right, next question is, are ions present? And none of these are ions, so that's a definite no. Now, do all of the molecules have a dipole? Well, carbon tetrachloride doesn't, so not all of the molecules have a dipole. What's holding them together then is going to be London dispersion forces. Here is another example. Here we've got trichloromethane and water. Do some of these molecules have a dipole? I already said trichloromethane has a dipole, so of course some of them do. Next question, are ions present? None of these are ions, so the answer is no. Do all of the molecules have a dipole? Again, we know that trichloromethane has one. Does water have one? Yes, it looks like that. So the next question is, do all the molecules have a strong dipole like NH or OH? Now, water has OH bonds. Do we have an NH or an OH or any sort of bond like that in the other molecule, in trichloromethane? The answer is no. So we've got dipole-dipole forces. That's what's holding this system together. And so actually what we're going to see when we get these two molecules together is something's going to rotate so that we have a positive end next to a negative end and vice versa. The reason we care about intermolecular forces is because physical states of matter are dependent on intermolecular forces. If you think about what you learned about solids, liquids, and gases, you know, even back in elementary school, we say solids have a fixed shape and a fixed volume, right? You can't compress solids. You can't change their shape. Liquids have a fixed volume. You can't squeeze water down, but they don't have a fixed shape. So you can pour it from one container to another and it changes its shape. A gas has no fixed shape and no fixed volume. Well, gases basically have no intermolecular forces holding them together. That's in the definition of an ideal gas, if you think back to your gas chapter. Liquids have intermolecular forces holding them together, but they're not very strong, relatively speaking. They're not very strong, and so you can't push things together. They're held together with very little space between them, so there's nowhere to compress. But the bonds are weak enough that you can rearrange things. Solids have many intermolecular forces holding them in shape, and that's why you can't compress them, and that's why you can't change their shape. So In a nutshell, intermolecular forces are basically forces that are kind of bond-like in that they're electrostatic attractions, but they're much weaker than covalent and ionic bonds. They're strong enough to hold molecules together, but they're not as strong as the forces that make the molecules themselves. I hope this was helpful, and I'll see you again soon.